All right, so yesterday we left off talking about sensitivity and the need for some of you to toughen up and stop crying. No, that wasn't it. It's okay for you to cry. Show little feelings. What's that?
Just in your car.
It's just a new car?
Yeah, just in your car.
Oh, just in your car. Yes. Yes, that is where crying should happen. In your car on the way home. That's where I do all of my good crying. All right, we talked about sensitivity. And sensitivity was described as, anybody remember?
The amount of current flow needed to create a full-scale deflection?
That is correct. And then we moved on to the sensitivity in terms of resistance. And we talked about the Simpson meter has a DC voltage sensitivity. DC voltage. And they describe it as 20,000 ohms per volt. And I guess the reason why I bring this up is, it's like, what does that mean? Why do I care? Well, you're probably going to move on to a digital voltmeter, so you don't care. It doesn't matter. But this is kind of a cool exercise, and oh, wait a minute. I forgot I wanted to do something. All right, back to our regularly scheduled program. All right, so the Simpson meter has 20,000 ohms per volt. All right, and so what does that mean? Well, let me see if I do this correctly here. That matters because, all right, so we just did a little bit of Ohm's law there off camera. So we'll do a little bit of more Ohm's law. And see what kind of fun stuff you can do once you start learning Ohm's law. So, all right, so we have E, I, and R, because if I don't do it this way, I'll be sorry I didn't do it. E, I, and R, and then we'll have E, I, and R over here. And this particular example I thought was pretty cool. It gave me 100 volts. And let me see. 100 volt. And R1 is 100,000 ohms. And R2 is another 100,000 ohms. All right, so we got two of them in series. So what is my total ohmage there?
200,000.
Okay, we'll put 200k ohms, and the current flow is then,
Divided by R.
this is where you jump in here and help me out with this, because you know.
Half a million.
Fresh sounds. Half a milliamp. 0.5 milliamps. Let me see. Okay. What's the voltage drop across each one? 50 and 50. Well, how do I know that? Well, because it's 100 divided by 2, because they're equal. They're the same. So that'd be 0.5 milliamps. 0.5 milliamps. All right. So let me see. Let's say that we have a let's do it this way first. We're going to connect a voltmeter right here. Put it right here, voltmeter. And it's the Simpson meter. And so Simpson meter has a voltage drop of what?
20,000 ohms per volt.
How many volts I got?
50.
So what is my resistance?
100,000. Wait.
Oh, wait a minute. So 20,000 ohms per volt. So what's that?
What's the setting on your meter?
50. Let's say 50.
Okay.
Actually be, say 100, let me see. I'm doing this out of order now. Yeah, what's my resistance? We'll say it's on the 100 scale, the 100 volt scale, 100 volt scale.
100 times 20,000.
So what is my resistance of the voltmeter? Everybody with me?
Yeah.
Or am I lost? Did I lose you? You got a Simpson meter that's 20,000 ohms per every volt that goes through it. And I'm going to tell you we're going to have a 100 ohms, 100 volt scale, so we're just going to make it easy. We're going to say it's the 100 volt scale, so the resistance of the meter is how much?
10.
So 100 volts times 20,000. So the resistance is 2 megs, so that's 2 million. 2 million ohms. All right, 2 million ohms. Now this is now in parallel with this. So what is the voltage up here?
50.
50 volts. How many amps did I steal from that? 50 microamps. So, wow, 50 micros. That's 1, 2, 3, 4, 5, 6, 5. Correct? I didn't really change that very much, did it? So if we were, let me think, if we were to take a look at, and that's the point of having this high resistance. So I know one of the things that some of you have done is, you know, especially on your parallel or series parallel circuits, you disconnect half the circuit and then measure what's left and say, well, that's the current flowing through it. Well, yeah, that's the current flowing through R1 now because you've taken 3, 4, 5, 6, and 7 and pushed it off the end of the table. Right? And I say, well, you can't do that because now you've rearranged the whole circuit. Well, the same thing happens that if you take a voltmeter that has a very low ohms per volt and stick it in here, it's going to change everything. So let me think here.
Question.
Yeah.
Yes, that number doesn't seem correct for the current. It should be 0.000025.
Yep.
All right. I didn't do the math. I just listened to you guys.
So 5 zeros, 25. Or 2.5 negative.
The other thing is you're not, no longer going to get 50 volts across that.
Not.
Microamps. 2.5 microamps.
Well, 2.5 microamps. All right. But are we really going to get 50 volts? Well, let's kind of dissect what we just did here.
I think it's 25 microamps.
Sorry, 25
Yeah.
microamps. My bad. 25. What's this?
You got some freaking number here. I'm going to start doing it myself. Jeez. All right. And then you can say yes or no. All right. But let's dissect this out a little bit and go, well, wait a minute. Wait a minute. We've kind of changed things here, haven't we? So EI and R, EI and R. We're going to just move it over and say, what did we really do? Well, we still have 100K right there. How much do we have here? 95K? 95K. 95K. So if that's 95K, do you see what we did there?
No, I'm what?
Oh, thank you for saying that. When you hooked up this voltmeter in parallel, now don't think of it as a voltmeter. Suddenly think about, I just put a resistor here in parallel. And that resistor is 2 million ohms in parallel with 100,000. What did that really do? So I probably shouldn't have done this right here is what I should have done. Just left that alone and just said, let's reevaluate the circuit and say, okay, we just put 2 million in parallel. So 2 million x minus 1 plus 100,000 x minus 1 equals 95. Well, now we can look at it and go, wait a minute, if this is 95 and that's 100, then we'll do it right over here. What is my total? Now my total is 195K. All right. I still have 100 volts. What is my current flow? Oops, learn a lesson here. What'd you get?
112 microwatts.
Get 3 zeros and a 5?
Yes.
Okay, 0005. Or 0.5 milliamps. So it's pretty much the same, We still have the 100 volt, 195. What is my voltage drop here? Well, since it's the same, 0.5 milliamps, we're still going to get 50 here, but it's 0.5 milliamps. What's my voltage drop here?
0.5 times 95.
Yeah, do that. 47.5 volts. That can't be it. 47.
But you're no longer getting 50
475.
volts across your 100 k resistor.
That'd be true. What do you think? So we got still half an amp, 0.5 milliamp, 0.5 milliamp, 0.5 milliamp. That's still 100. That's 95. So that adds up to 50.
Well, the resistance on the one above it is not 100% accurate. It's 95,238.
Oh, that's right.
0.2, yeah, right.
238.
I would round it.
Yeah. So it's going to get you close to 50 right in there. The point is that I'm making right here is your resistance barely changed right here. So that's going to have a small effect to this. It's going to have, and now we're looking at rounding errors because we're using such very small numbers. So you follow that when you hook up the Simpson meter that has this large ohms per volt scale, you see how it doesn't really affect it all that much. But what happened if, dear Lord, I changed this and it was 1,000 ohms per volt. Well, then what would my R right here be? I'll do it right here.
100,000.
EI. How much?
100,000.
100,000. Why 100,000?
Because 1,000 times 100.
Everybody follow? So we're using a new meter now. Bought it at Harbor Freight. It's only 1,000 ohms per volt. We have it on the 100 volt scale. So 100 times 1,000 is 100,000. What is 100,000 in parallel with 100,000?
50,000.
50,000. I'm going to bring this way down here. So EIR. So that's 50,000. Now if we have 50,000 and EIR, and this will be my total EIR. Now 50,000. This one's still 100 because it was fixed, right? And we still said 100 volts because that's fixed. Now what's the circuit look like? You see where I'm at? Anybody lost? Yeah.
You're saying it's 1,000 or initially, it's 20,000 ohms per volt. And
Yeah.
you're multiplying that by 100. Why are you multiplying it by 100 and not by 50?
Because it's on that scale, and I said we're just going to go with that scale.
So the per volt is the
Even though
setting.
it's
The setting is the 100 volt. Yeah.
drop. It's not.
It's the-
not that. It's
The
setting.
setting of the meter.
All right.
So we're back down here, and I've redrawn the, yeah.
Sorry, so what would the resistance be on the digital meter?
Well, can we get to that in a minute?
Sorry.
Okay. So back to my cheap Harbor Freight meter. So I've got, let me see, where was I? Oh, so we've got 100,000 on the meter plus 100,000 on the resistor. So what does that equal total? The meter plus that
50,000.
In parallel,
in parallel,
to the 50,000.
50. I hope everybody's with me. Maybe I'm just going too fast. Who's completely lost doesn't even know what I'm talking about. Yeah.
I got 50,000.
Now 50,000. What's my R total?
150,000.
150,000. What's my current flow?
666 micrograms.
Say it louder.
666 micrograms.
660 microamps.
66.
666. And what did we have before? Now, when we started the circuit, you built this little circuit. You had 100 volts. You had 200 K ohms, and so you had half an amp flowing, right? So half a milliamp flowing. So you take this cheap meter and you put it across there. What does the current flow suddenly do?
Goes up.
It goes way up. Now it starts taking, and so that changed the circuit. That changes everything. So I mean, we can figure it out. 666 microamps and 666 microamps. What is my voltage drop on each one of them? E equals I times R. So it's 666 second EE to the negative 6, if you forgot,
33.33.
times 50,000 equals, what'd you get, 33.3?
Mm-hmm.
What's it supposed to be?
50.
50. You mathematically said, well, that should be 50. What is this one down here?
66.
Can I trust you? How much?
You can
66.7? Yeah, it would be about volts. What was it supposed to be?
50.
What was this supposed to be?
50.
You see what happens if you have a really cheap meter and you throw it in the system. You start creating all this havoc of things that are going on. All right, 8,
What's
9.
the price difference of the meters?
Well, Harbor Freight, they're usually free. And I don't mean to pick on Harbor Freight. There's nothing wrong with Harbor Freight.
Simpson meters are like 200.
250. Yeah, we just bought like 20 of them. All right. Or, how much is a fluke? No, flukes? No, they're super expensive. 350, 400 bucks. All right, so through all that, I ended up with point D, electronic or electronic VOM volt ohm meters do not have this issue. So I guess you just bypass all that, buy digital, and you're fine.
And the reason why they don't have it is because they have such a high ohms per volt.
Reason why they don't have what?
The
This issue?
yes.
They just do it differently. They don't have a meter movement.
Okay.
So if you don't have a meter movement, you don't have the coil, you don't have the stuff in it. You can use digital electronics where it just senses it through
Got
the
it.
digital electronics and doesn't touch the circuit at all. So then why are we using Simpson meters in here?
So we can impress people in the field.
So we can impress?
Yeah.
Yeah, so you can pass your oral practical.
Well, yeah, that, and then.
And it's embarrassing for a graduate of this program if they were to get out in the field and like, can't read it, I can't read an analog, anything. Gosh, Phil talks about, because he does flight training, and he said that they have all these people calling up going, hey, I'm a CFII looking for a teach in a school. You guys are all glass cockpit, right? And he's like, no, we're still around steam gauges. Yeah, I've never learned on a plane like that. I can't fly one. I mean, literally people just like, I can't work there because they can't fly an aircraft with round gauges anymore. So you don't want to be the equivalent of that as a mechanic. It's like, well, I can't read that anymore. I don't know how to read a meter, but not you guys. So anyway, yeah, if the load meter had low resistance, all the current would bypass the load and significantly change the circuit. So I'll write that. So if, what was I going to say? If the meter, trying to write nicely, meter had low resistance, low resistance, all current would bypass. Current, or most would bypass the load, and significantly change the circuit. And you don't want that. You don't want the tool you're using to change what your outcome is of the circuit. I guess it's also a good point to point out that if a voltmeter is placed in series in a circuit, what happens?
Avoid 0.
What'd you do to the circuit? Or you opened it and then you put the voltmeter in series. Yeah, but not an electronic, but a Simpson.
Oh, a Simpson.
Yeah.
It'll just look like a high resistor.
Yeah.
You get no current flow going through it.
You add significant resistance. Like in our example, if you're trying to read 100 volts and you accidentally put the meter in series, and you added, was that 2 million ohms? Well, then you just added 2 million ohms in your series circuit. Well, what that's going to do to your current flow? Well, it's going to drop down. So don't do that. All right. That was voltmeter. let's see, 6. Talk about ammeters. Is that better? A little thicker? Ammeter. Well, we already know that measures current flow. Measures current flow. Ammeter or amp meter, ammeter, works on the exact same principle as a voltmeter. So remember, a voltmeter is really an ammeter that's calibrated to read volts, correct? That should make sense to you. A voltmeter has current flowing through it, and how much current flows through it is how strong the magnet on the needle is. How strong the magnet on the needle is how far it makes the needle move. So really, it's the current flowing through it that makes it read something, but it's telling you volts because it's calibrated to read that. Now, an ammeter is going to do the same thing because it's just current flow going through it. The big exception is what? You should know this. Exception is that the ammeter is connected.
Series.
Yep.
So it has very low resistance.
Connected in series and has what?
Very low resistance.
Very low resistance. So if we went back up to this whole thing, this mess right here, just because it would be fun, and we say, well, wait a minute, let's do this. Let's just hook an ammeter up right here that has very low resistance. Well, it's just, I don't know what, 0.005 ohms. What does it do? It short circuits the resistor. So all the current comes out of here and says, well, you know what? 90 some percent of it's going to go this way and very little goes this way. So you short circuit it. And then this now takes a big load. Well, actually, yeah, then this will take what would be the voltage drop here? About 100 volts. So this turns into a 100 volt voltage drop. If you connect it across here, it does what? You pop the fuse because now you've just made a series circuit that has no ohms, or it has 0.005 ohms, and so it blows the circuit. So you guys wouldn't know about that because it hasn't happened to you yet. I mean, nobody's blown it like 3 times yet, have they? Yeah. We got at least one 3-timer in here. Where are you sitting? Yeah. There you are up front. So he's a good student. He sits up front. He fesses to it. It's okay. He's behind his own. Let's see. So these little coils inside of these meters, they can only handle very small amounts of current. So we'll say that for very small amounts of current, the internal coils, we'll say coils because there could be 2, can handle the load. Oh, it's not a big deal. But if you want to increase that load, and for our purposes we'll say about 10 milliamps, if you were to put more than 10 milliamps through the little meter coils, what would you do to those little coils?
They act like a fuse.
It would look a lot like Sherman's project today. It would act like a fuse. And a fuse does what? That was a good answer. What happens when you put too much current through a fuse? And then what do you do with that? You throw it away. So if you put too much current through the coils of the meter, you throw it away. All right. So I was doing something on somebody asked me in this house, hey, does the 220 work for the dryer? And I thought, I don't know, man. I don't have anything to plug in the two. In my car, my father-in-law had gone to Harbor Freight and bought something and had a free voltmeter. Yeah, they work for, stick it, does it work? And I thought, all I gotta do is go get it. And guess what I left it on? Amps. Oh, jeez. Yeah, it's on. I don't know how on it is, but that's garbage. So, I mean, it worked. It did. It was just a single-use voltmeter. So don't feel bad. So, see? Okay, for currents. Oh, damn it. Over, say, 10 milliamps, a shunt is used. A shunt. Now, you've heard the expression, shunt the front door. That's what they're talking about right there. Is that not the expression?
Yeah. That's what I get from it.
Shunt the, never mind. Something else. All right, so what is a shunt? Well, parallel becomes too difficult to say and to spell, so shunt means parallel. So shunt is the same thing as parallel. So, oh, I have that in here. Good to do. So I was just saying, I'm going to write it, but that's going to screw up my timeline, or my outline. But shunt simply means parallel. So you're going to see that word, like a shunt wound motor, a shunt wound generator. What does that mean? It means it's parallel. Medical term too. Install a shunt means something parallel to something else. So what they're saying in this case, a parallel resistor is used. So if I want to put more than 10 milliamps through this meter, then I have to use a parallel resistor that's going to bleed off and use up more current and leave no more than 10 milliamps to go through my meter. So you want current to go this way, just a little tiny bit to go that way. So, all right. So think of a shunt as a bypass. All right, fun with numbers. So consider an ammeter. An ammeter that requires 0.01 amp to make a full scale deflection. And has a 5 ohm meter movement. Needle movement coil. I think I have a picture. There we go. Does that match up what I said? 5 ohm needle movement coil. Yep. Doesn't say that, but we'll put it here. It takes 0.01 amp to bring it all the way over here to the 30. All right, got it? All right. Let's see. Therefore, how many volts does it take to make a full scale deflection? You're thinking, how would I know something like that? I don't know. I'm asking how many volts it's going to take to do something. But what have I told you? I have told you so far that it has 5 ohms, and I told you that it takes how many amps to make a full scale deflection? 0.01. 0.01 amps. So how many volts does it take to make full scale deflection? Look at all the stuff you know right now, 0.05. Okay, at this point in the class, you got to be aware, especially once you finish your project where you're just doing your resistors, that everything's going to come at you, but nothing has changed. Everything is the same. It's just a different question. It's, what's the current flow? Oh, well, I know the resistance and I'll measure voltage. Or I know the voltage, I'll measure resistance. It's always going to be two things to find the third. The third, I'm going to always ask you for the impossible. And so what does that mean? Like if I ask you for the impossible voltage, what do you need to find out? The what?
Current flow resistance.
Current flow resistance. If I ask you the impossible current flow, then all you need to find out is voltage resistance. If I ask you the impossible resistance. Right? So you're doing something, I say, what's the resistance of that? And you go, you can't unplug it. What are you going to do?
Figure out the resistance, or figure out the amps, or the two other whatever you
The two other whatever is the best answer I can. Yes, the two other whatever is correct. It's always going to be that simple. That's, if you can remember that, there's almost nothing that you can't solve very quickly. I'll never ask you anything really harder than that. It's just going to be a weird thing. We have to go, what the hell are you talking about? All right. Okay. So, let me see. All right. If we want to measure up to 30 amps, oh man, I got to measure something on my 30 amp scale. All right. This needle can only handle 0.01 amp. So what am I going to do? So let me see. Let me go back to something here. Let me see. If we do something that makes a little more sense here. So we've got a needle movement. Here's my needle. And it was 5? 5. And I told you that we're going to have to put something in a shunt, which means it's in parallel. Okay. So I know I've got coming into it 30 amps. What is this resistor got to be right here? Well, to make things easy, what was the most current flow that can go through the needle? 0.01. And that's full scale. So we can go there, right? Hey, the most I can do is 0.01 amp. Well, then what is my shunt going to be? How many, what are we trying to figure out here? I want to know what this R is. So this is how many amps are going to flow through this shunt resistor?
29.99.
29.99 amps. Okay. Where do we want to go from here now?
Same volt, 0.05 volts.
Okay. 0.05 volt. We solve for that. It's parallel, so what is this voltage here? 0.05 volts. What is my resistance? Point 0.0167 ohms. You're really close. There you go. All you gotta do is remember that. What did you tell me? Just missed a 0. So let's just double check that. So for those that may not remember, it's EIR. So we want to find R. So it's E 0.05 divided by 29.99 equals 0.001667. What? You accidentally did 05? 0.5. Okay, that's okay. You got the idea though, right?
Yeah.
You did. Good job. All right. How hard was that? You see the question? So I could do the same thing. I could say, same information. 0.01 amps does what?
Full scale.
Full scale deflection. The meter movement is how many ohms? 5 ohms. Okay, so I've got my meter movement. I've got my shunt resistor. I am going to measure 3 amps. What is the value of that resistor? This is on the test. Some of you, oh shit, woke up. So what am I going to do? Same thing I always do. E, I, and R. E, I, R. I'll do it over here. E, I, R, in case I want it. All right. I said it's 0.01 amps. I said it's 5 ohms. So that means E, which hasn't really changed, is 0.05 volts. All right. It's in parallel. See the parallel? So what do I know about this one down here, this resistor? What is the voltage drop? 0.05. I said the total is 3 amps, so therefore the amps is going to divide between these two. If 0.01 goes here, then it's got to be 2.99 amps is right there. Therefore my resistance is 0.0167 ohms. What? You're just ahead of your time.
Yeah, I'm working ahead.
All right, one more. What if the full scale deflection, full scale deflection is, let me see. What if full scale deflection was 8? That doesn't make any sense what I wrote. Full scale 60 amps. I don't know what the hell I was thinking. I guess we'll just say same question, but what if it was 60 amps? We can do that. What if it's 60 amps? I got to measure 60 amps. So EIR. We know it's 0.01. We know it's 5. We know it's 0.05. Then this is going to, I is going to be, or 0.05. I is how much? 59.99. Therefore, the resistance is
0.00083
let me see.
0.0083.
Let's just check. 0.05 divided by 59.99 equals 123.833.472. That's exactly what you said.
So on the test, you'll give us possibly different,
Possibly,
obviously different numbers as far as the.
you'll be given full scale amps.
Uh-huh.
You'll be given movement resistance.
Okay. Of the needle.
Yep.
Okay.
All right, let me see what we got here. Did that. There we go. Ohm meter. Let's see. Ammeter has very low resistance. It's placed in series because of low resistance. If placed in parallel, the current will want to flow through the meter and blow the fuse. Basically, installing an ammeter in parallel will short out the selection connected. All right, let's talk about the ohm meter.
Good time for a break.
Yep.